Welcome fellow explorers to Project Makirraji. In the last episode, we saw how the 6 pioneers that colonized land on Makirraji diversified to form many thriving ecosystems. In this episode, we will see how these creatures evolved to conquer some of the harshest environments on Makirraji. Over tens of thousands of years, the continents of Makirraji have been slowly moving. The continents of Kaifo and Dexterra have been gradually pulling away from each other, forming a small sea in between the two continents. The gap between the continents is not large enough for any significant biological changes on either one. At the same time, Nymphus has been slowly drifting upwards toward Makirraji's equator. All these continental movements have shaped the landscape, trenching the oceans and pushing up mountains on the continents. These mountains have the ability to block the advance of moist air masses from the sea, creating large rain shadows. This causes inland areas to be deprived of moisture, creating deserts closer to the equator and tundras near the poles. Makirraji lies on the outer edges of Solarae's habitable zone, meaning it is on average much cooler than Verdantara or Earth. This would likely affect the distribution of certain biomes. The deserts may be cooler than Earth's and may also be confined to areas close to the equator. Tundras, however, may be more widespread, occurring far past the planet's poles. Some areas of the continent exposed to these extreme biomes alongside the coasts may experience seasonal rainfall or even monsoons. All these habitats will experience some of the most extreme temperatures on the planet, leading to a lower biodiversity. However, these harsh conditions may present themselves as opportunities for a select few clades. The seasonal areas of Kaifora may experience periods of drought followed by periods of substantial rainfall. Plants in these regions will have to adapt to the shift in climate. During the dry seasons, water conservation is key. To this end, the terra tegro of these regions may develop large bulbous bodies to store water. On a cellular level, these plants may have cells specifically used to store water. These cells could make up an organ of sorts called the hydrosphere. This organ will allow these plants to store water for months at a time. The leaves of these plants may need to undergo an adaptation to their structure. Larger leaves with more surface area radiate water faster through transpiration, the process by which water evaporates through the leaves of the plant. To solve this issue, the leaves of the plants may become slender, needle-like structures. These plants, which we'll call the Tydraphyta, will compose the dominant foliage group in the seasonal areas. Herbivores such as the Devirdants and the Volumare may congregate in massive herds during the wet season. However, once the dry season comes, it may be easier to simply move to more bountiful areas, rather than to tough it out until the rains return. These mass migrations may prompt predators such as the Cicydonts to leave with their prey, leaving the land barren of life. However, the absence of any competition during these times may prompt some creatures to live in these areas full-time. Perhaps some Volumare may shrink in size, becoming adaptable generalists. Their faces may elongate, being used as a shovel to unearth roots and other edibles. While these animals may spend most of their time foraging for food, under particularly extreme conditions, they may call upon one particular adaptation to help them weather extremely harsh conditions. On Earth, many separate clades have evolved forms of dormancy, with each serving a particular function. Estivation is a form of dormancy in response to hot, dry conditions. These hippopods may evolve an analog's behavior, burying themselves under the soil to weather the worst of the dry season. We'll call this clade the Xalicapods. On nymphas, the seasonal areas may be slightly different. A large portion of the continent is in close proximity to the equator. The warmer conditions here may allow for the formations of seasonal monsoons. These monsoons would flood the land, creating vast interconnected waterways. The dry seasons in these areas will be much shorter than on Kaifora. Plants living here may face many of the same challenges as the Tydraphyta. They may also converge on the same solutions. The Itinedidont of these regions may develop large bulbous bodies to store water and nutrients. Their gas sacs may emanate from small stalks attached to the main plant body. However, their gas sacs, somewhat analogous to leaves, may present a problem. Their gas sacs contribute a significant amount of surface area to the plant, thus enhancing transpiration. To resolve this issue, these plants may find a way to reduce their surface area during the dry season. To achieve this, they may temporarily lose their gas sacs during the dry season and grow them back once the rains return. This adaptation would leave the lands barren of foliage, with only large bulbs sticking out of the ground. We'll call these adaptable plants the Baealdophyta. Like on Kaifora, there will be many migratory animals that only stay during the wet season. However, some creatures may find a way to sit out the dry season. Perhaps a group of Veluridolla may evolve a prolonged form of estivation. During the wet season, these creatures stock up on nutrients, feeding on organisms such as the Baealdophyta or the Heteromorpha, storing excess nutrients in a specialized lump on their backs. This nutrient reserve would provide sustenance during a prolonged period of inactivity. When the dry season arrives, these creatures will seek out suitable locations to dig burrows. Once their burrows are complete, they would seal themselves inside, entering a dormant state. During this estivation period, the stored nutrients would gradually be depleted. With the return of the wet season, they would emerge from their burrows, ready to replenish their nutrient stores and continue their life cycle. We will call these organisms the Gulgadollids. Deserts, among the most unforgiving environments on Earth, are characterized by scorching temperatures and a dearth of water. Any organism daring to inhabit these inhospitable regions must possess extraordinary adaptations to survive. On Kaifora, the Tydraphyta are already somewhat pre-adapted to desert conditions, thanks to their drought-resistant leaves and water-storing hydrospheres. To further thrive in the harsh desert conditions, these maxiphytes may undergo additional evolutionary changes. They may experience a reduction in overall size, minimizing the surface area exposed to the scorching sun. Additionally, their leaves might become more bulbous, enabling them to store even greater quantities of water and other vital resources. Reproduction poses a significant hurdle for desert-dwelling plants. Deserts are characterized by vast, open spaces with few plants scattered throughout. This means that the chances of wind carrying pollen from one plant to another are significantly lower compared to denser environments. Therefore, unlike their wind-dispersed ancestors, these maxiphytes must find an alternative strategy to ensure the continuation of their lineage. To overcome this challenge, the maxiphytes may turn to animal-assisted pollination. On Earth, there are many forms of animal-assisted pollination. Regardless of the method, all forms of animal-assisted pollination require the plant to attract an animal in some way. The oases these plants grow around serve as vital water sources, attracting various desert animals. Capitalizing on this, the plants might develop a unique reproductive strategy, a tall stalk adorned with tiny, barbed spines. These spines carry the male gametes of the plant. When an animal approaches the oasis to drink, the spines can become embedded in skin. As the animal moves to other oases, the spines may dislodge, potentially transferring pollen to another of the same species, leading to successful pollination. This targeted method of animal pollination offers a significantly higher success rate than wind dispersal. We'll call these plants the Areaphyta. As the Areaphyta spread throughout Caiphorus deserts, they would create new opportunities for various clades to colonize these previously inhospitable regions. While the desert's harsh conditions preclude most organisms, those that are able to adapt find completely vacant niches. Desert animals tend to be small, as larger bodies generate more heat and have a larger surface area relative to body size, allowing for more efficient heat dissipation. This adaptation helps to regulate body temperature in the scorching desert environment. A group of small devirdants, naturally more resistant to heat stress, could potentially thrive in the desert. To navigate the vast distances between food sources, these desert-dwelling devirdants might evolve longer legs with wider feet to prevent sinking into the sand. These adaptations would enhance their mobility and energy efficiency in the challenging desert terrain. Desert winds can carry sand particles that can damage an animal's eyes. To protect their vision, these devirdants might develop a mechanism to retract their eyes into their sockets. This could involve a ring of muscle surrounding the eye, similar to how some animals can partially or completely close their eyes. When faced with a sandstorm, the devirdants could retract their eyes, shielding them from the abrasive particles. Like many desert animals on Earth, Caiphorus desert devirdants would likely develop highly efficient water filtration systems. These systems would allow them to extract the maximum amount of water from their food, minimizing the need to rely on external water sources. Some desert animals, such as the addax, have evolved such efficient systems that they can survive for extended periods without drinking, relying solely on the water obtained from their food. We'll call these creatures the Itinedidonts. Despite first impressions, living in the desert does come with some advantages. Predators in the deserts are almost non-existent. Actively hunting prey would expend far too many precious resources. Instead, most desert carnivores are scavengers, feeding on animals brought down by dehydration or heat stress. One clade poised to take up the role of desert scavengers are the Obdedorrids. These creatures are already generalist enough to take advantage of any and all available food sources. Like the Itinedidonts, these creatures may evolve smaller body sizes, thus decreasing their surface area. They may also develop efficient water filtration systems. However, these addodonts may undergo a shift in behavior as well. During the night, desert temperatures drop dramatically. On Earth, this results in most desert animals being either nocturnal, coming out only at night, or crepuscular, only being active during either dawn or dusk. Although this allows creatures to avoid the heat of day, it also requires them to undergo adaptations for low light conditions. These desert addodonts may develop larger eyes, by far the easiest way to increase the effectiveness of their night vision. The Obdedorrids, with their 3 pairs of eyes, may simply enlarge one pair of eyes, keeping the others small and unspecialized. Many nocturnal animals on Earth have evolved a tapetum lucidum, a reflective membrane that passes light back through the eye, increasing the rate of absorption. Thus these creatures may evolve something similar. Like the Itinedidonts, these creatures may evolve muscles that close over the eye, protecting it from the sand. Although the other 2 pairs of eyes aren't as specialized, they still serve to increase depth perception. However, these creatures' nocturnality requires them to sit out the heat of the day. Seeing as deserts are mostly open sand, these creatures will need to find a way to evade midday heat. Perhaps the most common solution among desert animals is fossoriality, adaptations for digging. This allows nocturnal animals to remain in the safety of the soil during the day. These adodonts would need to develop a few key adaptations to truly take up fossoriality. Powerful front limbs allow fossorial animals to dig through the substrate. The limbs of the Odentodonts may develop wide feet with 2 claws at the end, allowing them to break down substrate with ease. External structures such as ears or tails tend to be absent in fossorial species, seeing as they produce unnecessary drag. To this end, the bottom tentacle of these desert Odentodonts may become practically vestigial, no longer serving a purpose. These adaptations will allow the desert-dwelling Odentodonts to escape the blistering heat of the day, being protected in their burrows. However, once they do emerge to find food, they will need a way of locating it. Therefore, these creatures may develop enhanced olfactory receptors, allowing them to locate food over long distances. These Odentodonts may face their greatest challenge when it comes to reproduction. All sequidonts lay eggs, with a yolk inside. The developing young feed on the yolk, hatching after it has been depleted. However, the limited resources of the desert may strain the mother, potentially restricting her ability to provide enough yolk to sustain the young until they are fully developed. This could result in premature hatching, leaving the young with underdeveloped features such as underdeveloped eyes or unsolidified bones. These vulnerable offspring would be at a significant disadvantage in the harsh desert environment, facing increased predation and the challenges of survival without fully developed capabilities. To mitigate these risks, these Odentodonts may develop a simple form of parental care. The mother may lay her eggs in her burrow, keeping them safe until they hatch. Once they do hatch, the mother may bring them food such as chunks of meat from carcasses. She will care for the young until they are fully developed, at which point she will drive them out of the burrow. These adaptable adodonts are equipped to make the most out of their environment. Let's call them the Fosoctedonts. On nymphous deserts may be more widespread. Seeing as the bulk of the continent is around the equator, it may be warmer on average than on Kyphora. The deserts of Nymphus are perhaps some of the harshest on the planet. Any foliage that dare grow here would be quickly snuffed out. However, one clade of Areaphyta may find a pace in this harsh environment. To withstand the extreme conditions of the desert, these plants have developed a unique growth strategy. When a seed germinates in the sand, it utilizes its stored nutrients to grow a large, bulbous structure with a robust root system. During this time, the plant enters a kind of dormant state. This dormant state allows the plant to conserve water and energy until it has gathered sufficient resources for the next stage of its life cycle. Once the plant is ready, it will sprout a long, flexible stalk. At the end of the plant stalk is its one and only gas sac. Once the stalk has finished growing, the plant will begin pollination. In order to pollinate others of its species, these plants may also rely on the water they grow around. When they are disturbed by an animal, they will let out a puff of pollen that sticks to the animal. The animal then brings the pollen to another plant and fertilization is complete. After successful pollination, the plant begins producing large, bulky seeds. These seeds are stored within the gas sac, which eventually detaches from the plant body, allowing the seeds to be dispersed by the wind. Interestingly, the behavior of the gas sac is influenced by the competitive environment surrounding the parent plant. If the parent plant faced minimal competition during its lifetime, the gas sac will contain minimal gas, resulting in a limited dispersal distance for the seeds. However, if the parent plant experienced intense competition, the gas sac will be inflated with more gas, allowing the seeds to be carried farther away. This adaptive mechanism helps to ensure that these plants can colonize new areas, reducing the risk of overcrowding and competition for resources. We'll call these strange plants the Fluvutanagile. As these plants populate the desert, they will allow other animals to colonize this harsh environment as well. The dollipods, with their tough, scaly skin, may be prime candidates for desert colonization. Their scaly skin is extremely resistant to water loss, and it can protect against flying sand particles. Their lack of internal support doesn't allow them to get extremely large, but that isn't a problem, as, in the desert, it's beneficial to be small. However, several key adaptations may be key to these creatures' survival. Becoming smaller isn't the only way to increase surface area. Many desert creatures seen on Earth develop specialized structures such as enlarged ears or dewlaps. These desert dollipods may evolve a similar yet more extravagant form of thermal regulation. They may evolve a sail. Several creatures seen on Earth, such as the extinct Dimetrodon or the famous Spinosaurus, are known to have had sails. Although we don't fully understand why these creatures had these structures, it is highly likely they used them to regulate temperature. In these dollipods, the sail may be composed of elongated vertebrae, connected with thin flaps of skin. The skin on the sail would be packed with blood vessels to increase the rate of heat exchange. These creatures may also have wider feet to avoid sinking into the sand. Although their scales protect their body from flying debris, their eyes and respiratory passageways are still at risk. To eliminate this issue, these creatures may evolve specialized muscles to close over the eyes, similar to the eyelids of many Earth animals. As added defense, these creatures may evolve a specialized kind of scale. These scales would be small and thin. They would be used to catch debris before it could damage the creature. These scales would be found near the eye and surrounding the respiratory passageways. We'll call these small desert dwellers the Veluridolla. Perhaps a clade of Proledont may find themselves in the desert. These creatures may become desert scavengers, feeding on whatever they can find. These creatures may be crepuscular, meaning they are primarily active during twilight hours. The rotation speed of Makirraji may be slower than here on Earth. This is because during Makirraji's formation it collided with Nucesto. The angle and force of the collision slowed down the planet's rotational speed. The slow rotation or Makirraji will lengthen the dawn and dusk, allowing these creatures to get more done in their waking hours. These creatures may need a way to keep cool. Even though the twilight periods are cooler than midday, they are still quite hot. Therefore, these creatures may need a way to increase their surface area. They may adapt loose skin on their undersides to form a dewlap. This thin membrane of skin may be riddled with blood vessels, increasing the rate of heat exchange. These creatures would need a way to sit out the heat of midday. Unlike the Fosoctedonts, these creatures' unique limb configuration may not lend them to a burrowing lifestyle. Instead, they may use the claws on their feet to dig a small depression in the sand. They will then use their slender bodies to bury themselves beneath the sand. This would allow them to sit out the heat of midday and remain hidden from potential predators. However, these creatures' eyes and respiratory openings would be exposed to the sand. In order to protect the eyes, these creatures may evolve specialized sockets within the skull. Specialized muscles may activate when the creature buries itself. These muscles push the eyes into these sockets, with a flap of skin covering them. This would protect the eyes, but the breathing passageways would still be exposed. To solve this issue, these creatures' respiratory openings have migrated to the tops of their bodies. Therefore, the respiratory openings could be exposed to the air, keeping the rest of the body submerged. These creatures could bury themselves anywhere. Thus, they may not have a designated home, allowing them to live a nomadic lifestyle. We'll call these creatures the Psammoterrids. As we move closer to the poles, temperatures quickly decline. Makirraji's overall cooler temperature allows for the formation of vast stretches of tundra. These areas experience mild summers and long extremely cold winters. Many migratory species may live here during the summer months, leaving with the arrival of winter. The Tydraphyta may comprise the majority of the vegetation here, seeing as they are accustomed to extreme conditions. Unlike in the desert, it is in an animal's best interest to keep as much body heat as possible. Therefore, the animals in these habitats would tend to be bulky creatures lacking in any major external structures. The Divierdonts, being the largest creatures on Makirraji, have an advantage in this regard, as their large sizes aid them in reserving body heat. This is sometimes called gigantothermy, where a creature keeps itself warm through size alone. As the Divierdonts move further northward, they will inevitably attract predators such as the Crassodonts. As these clades move northward, the effects of their environment would become more pronounced. Their bodies may become rounder with shorter, thicker tentacles. They may also become larger, with the tundra Divierdonts being the largest animals yet seen on Makirraji. These creatures will become the dominant inhabitants of the tundra. We'll call them the Crassodonts and the Chiledonts. Despite their adaptations, most species in these clades may only inhabit the tundras during the summer. The challenges of winter are much greater than on Earth, with only the toughest of creatures being able to weather the harsh environment. As we venture deeper into the Arctic, we find areas where it is freezing cold all year round. These regions would be completely void of the dominant tundra megafauna. This may allow other animals to take up residence in these regions. In the deep Arctic, it is of utmost importance to keep as much heat as possible. Perhaps a clade of Gulgadollid may adapt to these icy regions. As previously mentioned, it is of extreme importance to keep as much heat as possible. One way to accomplish this is to evolve thick layers of fat, therefore these creatures may do just that. Fat is a poor conductor of heat and will thus trap the heat inside the body. However, fat alone may not be enough to weather Makirraji's harsh conditions. Air in and of itself is a very effective insulator, so another method of staying warm is to trap a layer of air near the body. In nature, we see this most commonly accomplished with some kind of specialized body covering, such as fur or feathers. The aquatic Veluridolla from which these creatures descend had teeth which some of their ancestors still have today. While not as apparent, these creatures do have flat teeth used to grind up food. However, they may also evolve another kind of tooth. Perhaps they develop a covering of thin hair-like teeth all around the body. These structures, unlike more conventional teeth, contain hundreds of tiny air bubbles, allowing them to trap even more air. These strange teeth, which I will henceforth refer to as Proledonts. These Proledonts, along with their layer of fat, will keep these creatures warm in even the coldest conditions. We will call this clade the Proledonts. However, these creatures are at their most vulnerable when they are young. The mother wouldn't be able to lay the eggs and then abandon them, because they could freeze far before hatching. Instead, these creatures' hind pairs of limbs may become cradles, keeping the eggs near the warmth of the mother. However, the mother may not be able to hold each individual egg. Perhaps they may resolve this issue by birthing the eggs covered in a slimy substance that quickly hardens when exposed to air. This substance would hold the eggs together, allowing their mother to keep track of them. These Proledonts will be some of the most successful creatures in the deep Arctic. Similarly to the desert, hypercarnivores are most commonly absent from the deep Arctic. Instead, carnivorous animals tend towards mesocarnivory, substituting their diet with plant matter when food is scarce. Perhaps a clade of extraladents may find themselves in the tundra. Their mesocarnivorous diet will allow them to subsist on plant matter if prey is scarce. These creatures may be smaller, as smaller sizes mean they require less food, and it shortens their developmental time, of which every second counts. Their smaller bodies require them to develop methods of conserving every bit of precious body heat. They may develop an extremely thick layer of fat beneath the skin, preventing most heat from escaping. They may also evolve a form of fur strikingly similar to that of the Proledonts. They may evolve specialized teeth that grow around the body. But unlike the pylodonts of the Proledonts, these creatures' pylodonts serve an additional purpose aside from keeping them warm. These creatures' pylodonts are larger than those of the Proledonts and are covered in tiny bristles. This gives them an added form of protection, as if an opponent were to try to attack them, their pylodonts would block the attack and cause mild discomfort. Yet again, these creatures will need to resolve the issue of offspring survival. If the mother were to carry her eggs around, it would negatively affect her speed. These hunters rely on speed and agility to catch their prey, and carrying eggs around everywhere she goes would significantly hinder her hunting. The mother couldn't lay her eggs in a den, as when the young hatch, they may not yet have developed the thick layer of fat that keeps them warm. Instead, the mother may hold the eggs inside her body for a longer period of time. This would allow her to pay more attention to hunting instead of managing her eggs. The eggs would develop in the mother until a few days before they are set to hatch, at which point the mother may lay them in a carcass. This would give the young the fuel needed to build up a sufficient layer of fat and finish developing their coat of pylodonts. We'll call these creatures the Tectudonts. On Nymphus, tundras may be less widespread, but still very much present. Like on Kyphora, many migratory species inhabit the tundra during the summer, leaving with the arrival of winter. The Baealdophyta are pre-adapted to these harsh environments, perhaps shedding their leaves during the winter and entering a dormant state. Animals living here will have to cope with the extreme seasonal shifts and lack of abundant food. As the Tundavanerrid spread across the continent, they will eventually come to inhabit the tundra. As previously stated, animals in the tundra develop many different adaptations to deal with the cold temperatures. Animals in the tundra tend to be large and bulky in order to store body heat. These pressures may shape the tundra-dwelling Tundavanerrid. Their bodies may become lower to the ground, with short bulky legs. Their mouths may be positioned lower to the ground, allowing better access to the Baealdophyta. These creatures may also develop a thick layer of fat to conserve body heat. They may also have a fat reserve on their backs, to keep warm and to store nutrients that they could access at later dates. When these creatures are young, their fat layers are at their peaks, but as they grow older they rely more on their size to keep them warm. We'll call these creatures the Tundavanerrids. As the Tundavanerrids spread, their predators will follow. As the Lingurids follow their prey into the tundra, they will face the same evolutionary pressures as the Tundavanerrids. They may also converge on similar solutions. A bulky body and thick layer of fat keep these creatures warm. Their tongue has become bulkier to pierce the hide of their prey. If their tongue were to pierce the main body of its prey, it would be fatal. These creatures also have an added layer of insulation. They are covered in fine hairs. These creatures' freshwater ancestors had small hairs in their mouths to filter out food particles from the water. In most land-dwelling forms, these hairs can only be found around the mouth and their respiratory openings. However, in these forms the hairs have spread across the entire body. Although they are most apparent on these creatures' backs, tiny hairs grow around most all of the body. These hairs give the tundra lingurids added protection from the cold and allow them to venture deeper into the Arctic to pursue more cold-resistant prey. We'll call this clade the Obdedorrids. In the deep Arctic, only the most adaptable of creatures can survive. It is for this reason that the Conterrids may take up residence here. Their adaptable lifestyle allows them to take advantage of every resource available. These Arctic Conterrids will need protective measures against the extreme cold. Firstly, they may evolve a layer of fat to keep warm. The fat would be particularly thick around the eyes, mouth, and respiratory openings. Their long, thin tongue is very susceptible to heat loss. Therefore, these creatures may opt to use it much less, instead relying on their powerful kicks and sharp claws to settle any disputes. However, these creatures may also evolve a coat of fur analogous to that of the Obdedorrids. Unlike the Obdedorrids, these creatures' fur is much larger and more numerous. Yet again, these creatures will face the challenge of reproduction. In this harsh environment, the mother can't simply lay her ootheca anywhere. To keep the ootheca safe, this clade may increase the amount of time the ootheca spends developing in the mother. Unlike the Tectudonts, which lay their eggs a few days before they actually hatch, these creatures' young hatch inside the mother, giving the appearance of live birth. This is called ovoviviparity. However, resources in the tundra are few and far between. This means the mother may not be able to supply enough yolk to last the whole of the young's development. This would result in the young hatching prematurely. In the harsh environment of the tundra, premature young would almost certainly die. Therefore, instead of relying on a limited yolk to last the whole of the young's development, these creatures may evolve something called metrotrophy, in which the mother supplies additional nutrients through a placenta-like organ. Although metrotrophy takes a higher toll on the mother, it does ensure that a higher percentage of the young will survive. We'll call these Arctic scavopods the Fracoterrids. The extreme climates found on Makirraji have spawned unique and resilient life forms that are well adapted and able to thrive in spite of limited resources and against all odds. From the barren tundras to the inhospitable deserts, life has found a foothold and defied the odds. As the continents of Makirraji continue their unhurried and centuries-long journey, unexpected changes will gradually shape the landscapes and the creatures that inhabit them. Join us next time when we will examine the lush and leafy rainforest regions of Makirraji, home to exotic species of plants, towering trees, and a biodiverse cornucopia of remarkable creatures. A huge thank you to all the artists on Discord who made fan art for this episode. Your contributions to this project are invaluable. If you want to join the Discord to chat, make fan art, or just get early access to some of the creatures coming in the next episode, then you can find the link in the description below. Thank you all so much for watching. Don't forget to subscribe, like, and share your thoughts on these incredible creatures.